Hey, this is Steven from LegitTechTutorials, and welcome back to my products design / product development series. So we're back working on the CNC Plasma Cutter table. This is video number 2. And so I was playing a few video games, looking through on my second screen here, on my right screen, looking through some plasma table images of different DIY plasma tables, and looking at what they have, also looking at CNC router parts, which is also a pretty popular table manufacturer for CNC routers, table routers, and also now plasma cutters, and I guess technically lasers if you want to do that, or water jet or whatever. You know, they could all kind of use the same table. But so I'm definitely leaning more towards using square tube, as I think it will be the best setup to where you have nice rigidity of the table, and you could reuse the rails as your guides instead of buying a second piece. So for example, if I wanted to run flat bar on top of the square rail, so you have a square rail and then you put a flat bar, like a 3-inch flat bar, 3 inch wide by 1/4 inch thick, and then all the way down the table, 8 feet. You'd have to weld that on top of that square bar. I mean the square tube, so you don't have really, that doesn't have enough rigidity to hold the table square, unless I did some sort of I-beam thing, which not a bad idea, I guess. Have a whole bunch of bar and then weld it into an I-beam, but it's gonna weigh just as much as just square tube, and a lot more money, because I want to spend, I've learned this from my first product with the multi-shooter, that the time shouldn't be spent in the frame. It should be spent in the electronics and the mechanical portions, right? So mainly, not so much the movement electronics, but more the cutting head, which obviously I'm going to go with a cheap cutting head, which is a Cut 50, which is like $200. But I don't want to spend a lot of money in the frame. I want to spend it in where it counts, where the cut counts. But the frame doesn't necessarily have to do much with the money that you're spending on it. It has to do with the time they spend on it to make sure that you have it squared up and little to no run out on either side, or any sort of racking. Because the main problem with these machines, mainly with these styles where you have the beam going across, is it racking, which is basically let's say that, so for the right hand rule, your hand goes down one of the axes, goes down the x-axis, and you curl to the y-axis, and your thumb of your right hand should be pointing up. That is a positive z-axis. So that's generally how they go. So in this case, the y-axis would be, let's say that your table is pushed up against a back wall of your shop or whatever. Your hand would be going down the x-axis, and your y would be going off to the left, and then your z is straight up. So let's say that your x-axis is straight down the table. Generally, that's what it's going to be. X-axis is going to be the long way, y-axis is the short way. So what will happen is the x-axis on one side of the table, on y0, so x is the long way, y is the short way. So on y0, right, which means that it hasn't progressed at all to the left on the table, it will be x 15 inches, and then on y 4 feet it will be x is 20 inches. So you have a cosine error there of 5 inches. So one side's 5 inches farther than the other side, and you'll know that when you start to cut out, for example, let's say you start to cut out a square for measuring stuff, and then you measure it on a good known square. It's not going to be square, because one side is kind of has a little bit of an angle to it, even though what you're drawing in your CAD file says that it's supposed to be straight, right? And yeah, so basically you're going to have that error, that repeatability error where depending on how long your parts are going to be more or less out of square. So if you're cutting a full 4 feet wide part all the way down the table, all 8 feet down the table, a diagonal line or a giant square or something, layout square, you're going to have a lot of run out. So we want as many bearings pretty much contacting the side of that square tube as possible. Let me see if I can show you guys a good one. This is kind of the one I was looking at. It's kind of small, but nice to see. And then I'll show you guys some CNC parts. So CNC router parts. So you see here, nice. And then this is all polished, which I'd probably do just to lower the friction on the wheels and also get rid of any sort of vibration as it goes over, because most likely I'm going to be getting this at the local Sims Metals, as that normally my dad used to work with them, so I get good deals from there. So this is going to be A36, and A36 has got kind of that weird surface, so most of this will probably be gone over. Sure, it's going to kind of knock some of the repeatability off, but that's fine by 1,000, 2,000. I just rather not have any sort of vibrations oscillate through this beam across. But you see how easy it is to have the this guy, how it is, where it's just box tubing, box tubing, box tubing, box tubing. So for this guy, I'm thinking for that guy, do the 3-inch plate, and then have the V bearings right on the side of the 3-inch plate. So pretty simple there, and then have a little an eye, like a have a little eye thing there that will have a angle iron that the motor, the stepper motor will attach to, and then that will just go up and down. So that's what I think is best, is the square tubing, and then make the frame out of the square tubing as well, and try to have as minimalist as a square tubing as possible. And then again on here you see how the bearings are contacted, but a main thing that I have to think about is what the slats or the ribs are going to look like, and where they're going to attach, and where's the cheapest and most efficient way to have the steel attached to it. One of the ways I was thinking is to cut into this guy and have the slats go directly in the square tubing. But the problem with that is that you're basically lowering your rigidity of that piece. So how tech shops did it is they had well, obviously everything on tech shop's one was aluminum extrusion, was box aluminum extrusion. And I think it was maybe 2 inches, maybe 2 inches wide, 3 inches wide, 3 by 3 inches wide, and then they have, you know, the slot where you could put T-nuts in there, and then they had a plate go down the bottom, and then they had the slat, they had the ribs go in there. So that's another way of doing it. Yeah, so that is one way of doing it. So maybe get a piece of A36 bar, the same exact A36 bar I use here, that goes all the way down the slats, and then cut some slots in there, and then try to find the largest blade that I could use to cut the slots in, or use figure out how I'm going to do that. Maybe have somebody cut it on the water jet so that the slats fit in there. Probably have somebody cut it on the water jet, because otherwise I would need to have a cold saw blade, and I don't really have access to one right now. And a fat cold saw blade, so those slats could be at least 1/8 inch, because I don't want them to bow too much in the middle, even though they were going to be lengthwise. So lengthwise they're not going to bend too much. And then all of this is going to be great for running static simulations on, to look at bending, which is what we're going to do in this video. We're going to run static bending to figure out exactly how big of this tubing that we need, what size tubing that we need, and what wall thickness that we need in order to get the most rigid, well, to minimize the bending in the middle, so we can minimize how many legs we have. So what I was thinking here, there's a few that use like trusses and stuff, but this is kind of what I was thinking. Just what it would be, 1, 2, 3, 4, 5, 6. 6 legs, so 1 leg per foot. So here's 1 leg, here's another leg at 4 feet. Here's 1 leg, another leg at 4 feet, and then another leg at 8 feet. It's the same way. So and then just 1 piece on top. Maybe not even this for the drag chain. Maybe or maybe not. What I would like to do is I would like it to almost come through maybe through the tubing. Through the tubing would be kind of nice. It came up and through the tubing. Maybe something to look into. Having it go through the tubing. And then like push a piece of steel up in there to plug it so it maintains its strength. But have a piece of wire go through the tubing, maybe get nice and clean instead of a heavy drag chain. Because these are probably going to be NEMA 17s or maybe small NEMA 23s to start out with. And then maybe go to geared NEMA 23s as you know, I use it and start to make money off it or whatever. So yeah, here's I don't know why it's so laggy. Something's going on. I probably should stop putting my PC to sleep and start turning it off fully. Anyways, so here's the idea of having this square flat plate. So, but I would have to buy the bar, and then I would have to buy the buy the flat plate. I would have to buy the square tube, and then buy the flat plate, and then weld the flat plate on top of the square tube, and then make sure I square up that flat plate so it goes perfectly in line. It's just a lot of work, rather than squaring it up once. So here's kind of the idea of what it would do. So this is just some square tube, and you cut the center out of it, and then you just run 4 bearings in there, and some other bearings here with a bolt welded across the top or whatever, or a nut welded across the top, and some slots cut in there. Easy to do on a mill, manual mill, which I have access to. So I'm thinking something like that. May or may not have something on the bottom, but and then have the top of the A36 where the slats are welded in here, right where these bearings don't hit, and these bearings clear right over the top. And then obviously have some room for the 4 foot by 8 foot sheet to be in there. Right, so that's kind of what I'm thinking here. I mean, you have a lot of extra stuff. You have the triangular tube, which I don't have any problem with. It is a good idea, the diamond, but if I were to build, I think that would definitely not be strong enough to hold up. And you see here, you have the square tube, and then you have this up, and then you have this, and you have this. You know, there's a lot of extra money spent. I mean, not a lot of extra money, especially A36. It's not a lot of extra money spent on that steel there, but definitely some extra money spent on steel. While here, this is like the bare minimum here of the expense here. And also the other way is a lot more welding, because you have to weld they don't really sell diamond shaped steel. They sell 2 angles, and you weld the 2 angles together, and then you have to line that up and blah 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 blah. So here's an idea, you know, kind of how you would box in the bottom to try to get all the gases out, and maybe box in the whole thing, or drape something over the whole thing and collect all the gas and get it out. Maybe put it in a separate room. Maybe put it in like a room with a drop-down door or something, so collect all the gas and siphon it all out. Because again, green engineers, I do kind of want to suction it all out. So here's like another idea of a table. So here's how it's welded. Another thing I need to decide is whether I weld it together or if it's assembled with bolts. Obviously bolts and nuts is going to be like 3 times the amount of work needed, because then you need to weld plates with holes in it, perfect holes in the back of these pieces here, and then you need to weld in nuts inside of the tube, right? Somehow weld nuts inside the tube so that they stay where they're supposed to be. So definitely not, because you probably don't want to thread even 1/4 inch wall or 1/8 inch wall of the square tube. So I'm thinking right now just weld it and then have to measure any sort of door where I build it so I could get it out of the place and get it into the new place. Alright, so let's go ahead and open Fusion. We're going to run some static analysis so that I can figure out what size tubing I need to ask Julian at Sims what size I need. And obviously, this might not be the perfect size, so we'll probably up the size and then go with that. Okay. So let's go into, let's start a new project, and then this is going to be called the CNC Plasma Table. And then this is my new one. Okay, so let's go ahead and create. So we're going to have two. One's going to be, let's start out with, let's say 2-inch. It's got to be at least 3 inches. 3 inches by 3 inch. And then let's see 1/8 wall. Let's see if, I don't know if I can get 1/4 inch wall. I'll have to see. So let's, like I said, just a 1/8 wall. 1/8 wall. And then this is going to be, let's say 8 feet. Let's say 4 feet. Okay, 4 feet. And this is going to be bodies sketch. It's going to be physical material. Steel, A36. Regular A36 structural steel. Simulation. Static stress. Okay. So then basically I'm going to put a maximum. Obviously this is going to be half and half, half on one side, half on the other side. But this one's going to take, let's say, a maximum of quarter. So let's say maybe 180 pounds. Let's just say 180 pounds on this one. Worst case scenario. You're going through big plate. Let's see what the CNC. So let's look at cut 50, 200 bucks. View details. I'm going to see what the maximum of 50 amps we cut. Probably don't want to go more than 50 amps for this one right now. What do we got? I don't know if it's going to tell me. Saying up to 12 millimeters is pretty high. That's almost 2 inches. Whoops, sorry. It's about half an inch. So let's say maximum. Let's say, however, we had half an inch. So let's see, steel weight. Okay, alloy steel. Select alloy. 41, whatever. Flat bar. Pieces 1. Gauge 0.5 inches. Width. So this is a 4 foot by 4 foot section because there's gonna be a leg here, so that's gonna take up quite a bit of this flex. So there's gonna be a leg after 4 feet. So it's going to be 4 feet. This one's in feet. 4 feet by 4 feet wide. That is 324 pounds for 4130 alloy steel. I don't think they have just regular steel. Oh, yeah, they do. Steel 836. Calculate. Okay, so it's actually a little bit heavier. So let's say that's 163 pounds. So that's divided in half. So half on this side, half on the other side. So let's put that in there. Constraints, structural constraints. So let's go ahead and put it at the very edge here. Actually, let's put it on his face. Cool, that will let me. There you go. That's face that's going to be welded. Okay. Alright, now let's put a load. This is going to be pounds. This is going to be 320, oh, 163. Yeah. 163. Okay, let's go ahead and solve it locally. So, this is 3 inch by 3 inch 5.125 inch wall. Test. Okay, solving here on my other screen. So let's see, I'm curious what this is for 8 inches. So that's 652 pounds, a total for all the way down. Alright, so actual minimum safety factor. This is actual deformation. So let's see the displacement we're talking about here. So we're talking about very low. That's it's 9 thou. Obviously most in the center. Okay, so this is 1/8 inch wall. So let's see. Let's run another one with let's see, duplicates. Oh, let's just file save as. This is 0.25 wall. Okay. Also, want to be very careful on this because I don't want to make it too heavy, right? Too heavy of steel, because it makes it very difficult to bring it around. Well, this is more displacement. That doesn't make any sense. I think it's under its own weight. Actually, that's another question. Let me turn on gravity. Turn gravity on. No, gravity is the other way. Reference geometry. I'll change that later. You get the idea. I just need to flip it around. Generally I don't work with gravity, so... Well, I mean, I mean in CAD. I don't work with oops. Whoa. And displacement and inches. So that is about 1 thou. About 1 thou in the center. And this one is about half that. 0.0133. 0. That is half of a thou. But let's see, back to the model. So first one's about a thou in the center, which, you know, obviously there's a lot more things that are going to hold it more rigid than that. Like this, even the slats I think are going to hold it more rigid. What about the, so what's the weight of this one? This is the 1/8 inch wall. It's going to weigh 113 ounces. So 113. 113. No, 313 divided by 16 is equal to 20 pounds. Does that sound about right? What about kilograms? Change this to I wonder if foot's what foot would give you. Pound mass, there you go. Yeah, 20 pounds. 20 pound mass. So it's 20 pounds. 1, 2, 3, 4, 5, 6, 6. It's 120 pounds. Plus another 3 feet. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, 13 across the center. Yeah. So another question is, can I go any lighter than that? So what about a what about duplicating this? File, save as. Save this as a 2 by 2 inch by 1/8 inch wall. Wait, what? Oh, this is foot. 0.2 inches. Oh, it's 2 inches. There you go. Because I'm not exactly sure what this other one is. This is definitely 3 inches there. This one could be 2 inches maybe. Let's run it again. So it's 3 thou. 3 thou in the center. For twice of its actual load. So what about what was its what's its standard load I'm looking at? 4 feet wide by 4 feet wide, 160. So this is the regular load that I'm looking at. Edit structural load. It's 80 pounds. 81.5 actually. So this is a 1/4 inch by 4 feet by 4 feet. One and a half thou. Maybe what I could do is I could run this size 2 inch by 2 inch and then somehow offload some of the weight to this cross member piece here. So normally they have the ribs going this way. Maybe have like an under piece here that goes underneath and holds it up, and put some of the weight off onto this piece here. That's interesting, because this way maybe properties 12 pounds. It's quite a bit less. And then file, save as. And let's try it. Let's cut the difference. Let's do one last simulation. What says this is less than the 3 inch? That does not make any sense. Oh no, this is less. So this is less than 1 thou. I think I'm cool with that. 2.5 inches. 2 inches is a little small, but 2.5 inches I think will be okay. 0.02048. 48. So it's 0.0008. So 0.8 thousandths of an inch. So that's pretty small. That's pretty small. I think that is definitely fine. Even the other one I think is fine. Even 2 inch to keep that weight down. This is 16 pounds. The other one 10 pounds. The other one's 12 pounds. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 13 times 12. It's 156 pounds. I'm happy with that. That's a nice lightweight machine there for a 2" by 2". So I'll give a call to Sims and see if we could price out some of that 2" by 2" by 2", or at least that he carries that, and then see if he has 2" by 2", 2" by 2.5 by 2.5, 3 or 3.5 eighth wall. I'm sure he's got eighth wall, that's for sure. But I think ½ an inch is gonna work. Alright, so this has been Steven from LegitTechTutorials. Thank you guys for watching. If you like this video, please subscribe for more videos like it in this series and our series as well. I'll see you guys in the next video. Thanks for watching. Take it easy. Peace.